All right, let's dive into one of the coolest, most clever tricks in the world of AI. We're talking about a technique that's responsible for making the chatbots and language models you use feel so incredibly fast and responsive.
You've totally seen this, right? You type a prompt into an AI, and there's that little pause, it's thinking, and then suddenly, whoosh, the words start pouring out. That initial delay isn't an accident. There's actually a really fascinating reason why that first word is always the hardest. So here's the core of the problem. It's just pure computational waste. See, for an AI to generate a new word, it has to look at all the words that came before it. And without any smart tricks, it literally recalculates the relationships between all of those previous words every single time it adds a new one. It's like having to reread a book from page 1 just to understand the next sentence. It's slow and it's super inefficient. So, to fix this, developers came up with a really brilliant first step, a technique called KV caching. And honestly, it completely changed the game for how fast AI inference could be. So what is this thing? Well, put simply, KV caching is basically a cheat sheet for the AI. Instead of throwing away all that hard work after calculating it once, the model stores the key results, we call them keys and values, in a special cache. Then, for the next word, it just pulls from that cache. No more rereading the whole book from the beginning. Okay, so here's the play-by-play. That first big pause when you're waiting for the first word, that's when the model is processing your entire prompt and saving all those important key and value numbers to its cache. Then, for every single new word it generates, it just grabs that cache data, mixes it with the info from the newest word, and bam, it spits out the next one. It then adds the new word's info to the cache and does it all over again. It's a really simple but super effective loop. And wow, when you put them side by side like this, the difference is it's night and day. Without caching, the model just gets more and more bogged down as the text gets longer. But with KV caching, it stays snappy and fast because the amount of new work it has to do with each step is tiny. And we're not talking about a small improvement here. In one benchmark, just using KV caching made the whole process over 5 times faster. That is a massive, massive leap in performance. But, and you knew there was a but, our story doesn't quite end there. Because like any good engineering story, fixing one problem revealed a totally new one. And this new problem wasn't about speed at all. It was about space. So it turns out that while KV caching is fantastic for speed, that cache of stored values takes up a huge amount of very, very expensive GPU memory. I mean, for a big model like Llama 370B, the cache for just one single user could eat up over 10 gigabytes. That severely limits how many people can use the service at the same time. Now, to make things worse, the old way of handling this was really clumsy. Since you don't know how long an AI's response is going to be, systems would just pre-allocate a huge continuous chunk of memory for every single user. This was incredibly wasteful. If a request was short, all that extra space in the block was just sitting there empty. That's internal fragmentation. And all the weirdly shaped gaps between these giant blocks created even more unusable memory, which we call external fragmentation. I mean, just look at this. It's kind of crazy when you see it laid out. In some of these older systems, only about 20% of the memory that was set aside for this cache was actually holding data. The other 80%? Pure waste. So we solved the speed problem, but we created this massive memory efficiency crisis. Okay, so what now? Well, this is where the real hero of our story comes in. A much more elegant solution that tackles this memory problem head-on. And it's actually inspired by a classic idea from computer science. It's called PagedAttention, and here's the genius of it. Instead of demanding one giant, unbroken chunk of memory, PagedAttention chops up the KV cache into lots of little, fixed-sized blocks, or pages. And the revolutionary part? These blocks don't need to be right next to each other. They can be scattered anywhere in memory where there's a free spot. And if this concept sounds a little familiar to you, well, it should. As the researchers behind this pointed out, this idea is directly inspired by virtual memory and paging, a core concept in operating systems that has been managing computer memory efficiently for decades. It's just a brilliant application of a time-tested idea to a brand new problem. This analogy just nails it perfectly. The old way, standard caching, is like booking a giant banquet hall for a party when you have no idea who's coming. You're going to end up with a ton of wasted space. PagedAttention, on the other hand, is like booking individual tables only as your guests actually arrive.
It's flexible, it's efficient, and there's pretty much zero wasted space.
So, we've got this super smart memory management system. What does it actually get us in the real world? Why does this all matter? Well, the results are kind of staggering.
By basically getting rid of all that memory waste, systems that use paged attention, like one called vLLM, can get 2 to 4 times higher throughput. Now, what that means in simple terms is they can handle 2 to 4 times as many users at the same time on the exact same hardware.
And look at the direct impact on speed. A task that might have taken 40 seconds before these optimizations now takes just 9. That is a game changer for the user experience. It's the difference between something feeling sluggish and something feeling instant.
And this chart just says it all, doesn't it? Let's go back to our memory waste problem. Remember those old systems hovering around 20 to 40% efficiency? Well, vLLM with paged attention hits an incredible 96.3% memory efficiency. They've practically eliminated the waste altogether.
So let's just quickly recap this whole journey, from that initial slow first word all the way to this final super elegant solution.
So what's the story to remember? We started with a simple problem. AIs were slow because they were redoing the same work over and over. KV caching came along and fixed the speed, but it created a huge memory problem. Then paged attention, an idea borrowed from classic computer science, came and solved the memory waste. And the final result is the fast, efficient, and scalable AI that we get to use every day.
And this all leaves us with a really fascinating question to think about. We just saw how a 50-year-old idea from operating systems became the key to unlocking the performance of modern AI. So as these models get bigger and more powerful, what other forgotten gems from the history of computer science are just sitting there, waiting to be rediscovered to solve the problems of tomorrow?